For this project, you're going to need a stump rocket, which you can find easily on Amazon. There are also some foam rockets included inside the package. And to calculate everything, you will need a scale to see the mass of the object and the distance reference like a ruler for the video measurement. You will also need a bottle of water to make sure your rocket heavier if you don't want it to lose control in the wind. Now let's go to find a part can do it. It comes with a pretty simple setup that a rocket launch at an angle at one side and landing on the other side. My nephew is going to help me do it. I had a 60-inch ruler, which is around 1.5 meter on the ground for the video distance reference. I will set the coordinate system like this, but you will see a big difference on Logger Pro because my camera was not parallel with the rocket. After that, I put the video in Logger Pro and calculate what I need to know. For example, the launch angle, the flight distance, the change of velocity and acceleration in vertical and horizontal directions. I will show everything that I can get as you can see on the screen, but remember that the values that you will get may be a little bit off due to the air resistance. I will talk about how to use Logger Pro in another video. Right now, my teammates are going to explain the experiment in detail using Newton's second law and Newton's third law.
Hello everyone, my name is Charity Liu, and I'll be going over the free body diagram of how the rocket launch will be observed in its free body diagram as a projectile motion. This motion has both an x and y direction. Drawing the free body diagram on the object, which is the rocket, the force applicable here would be the weight, which points downwards. The rocket doesn't touch the ground nor is attached to anything, so there is no friction involved. Note that air resistance may play a part in an actual rocket, but for our experiment, we will be disregarding the air resistance as we have not yet covered it. So the force that would be accounted for here would only be the weight of acting upon it. As it is a launched projectile motion, v initial x is essentially the same all the way through the problem. Only v initial y changes, becoming large to small, to 0 at the top, then becomes a negative.
This is the force diagram for the model rocket, and you can see there's only one force on it, which is the weight. So plugging this into Newton's second law, we have f of x equals 0 because there's no forces pushing it side to side, and the only force acting on it vertically is gravity, so turned out to be negative 9.8 meters per second is the acceleration. So we have a bunch of missing variables here when we want to look at like the different properties. So we need to find velocity, final, initial, and x, and the x final. So we're going to use some projectile equations for that. So we're going to use this equation to find the velocity initial, this one to find the velocity final, this one to find the final velocity of x, this one to solve for the final x position, and this is what we end up with.
Hi, my name is Tatiana Volner-Velandia, and I will be covering the topic of how Newton's third law relates to our experiment, which is the rocket launch. This will help us apply the third law to real-life situations, for example, understanding how real rockets launch into outer space. So first, what is Newton's third law of physics? The Latin translation of this law is, to every action there is always an equal and opposite reaction. In other words, the forces of two bodies on each other are always equal and are directed in opposite directions. So when it comes to our rocket experiment, when the rocket is pressurized with air, the action force of air comes out the bottom of the rocket and exerts an equal force. That propels the rocket upwards, which is in the opposite direction. Now, with a real rocket in space, there is nothing to push off of that will allow the rocket to accelerate. So, rockets utilize the combustion reaction in their fuel tanks. The reaction will force out gases at ultra-high velocities from the back of the rocket, and this action exerts a force on the particles, which in return propels the rocket in the opposite direction.